Thank you folks for coming out here tonight, braving the floodwaters out there. Flash flood warning that we have. Anyway, we're proud to have is that, nope, okay. Anyway, is that, okay, they found us. Good, good, okay. Anyway, we're proud to have Dr. Elizabeth MacDonald from Goddard Space Flight Center, although, well, you can tell them she's working remotely now in a much nicer place than Greenbelt, Maryland. Anyway, her background was she did her got her BS in physics from University of Washington there in Seattle. Wonderful place. My son wanted to go there and couldn't. And then went off to the University of New Hampshire to do her master's and PhD in aurora physics. She did sounding rockets. So she was helping with instruments that they launched from Alaska up into the Northern Lights and then back down and analyzed that. So she was studying the aurora, what caused it. And then she went off to Los Alamos. I guess that was a postdoc for to do further work on magnetosphere, what drives the aurora. And it was there that she discovered, after a particularly large storm, that there were all these reports on Twitter. And that inspired her to get started doing the Aurorasaurus citizen science project that she'll be talking about. And her other claim to fame is that when she went to NASA, was she started working again with citizen science, but also she was instrumental in the discovery, rediscovery, publicizing of a new aurora called Steve. I'll let her explain why it's called that. That was an aurora that had been hiding in plain sight for over 100 years. So a bunch of amateur aurora spotters up in Canada started posting about it on Facebook. So, and the interesting thing about that, as she may mention, is that it took a while for anyone to figure out what's causing this. And it turns out that it's tied into, and this was what, in the 2010s that Steve was, anyway, 2015. Okay, yeah, 2018. Come to find out, it's tied in with an ionospheric phenomenon that was first identified here at UTD back in the late 70s by Bill Hansen, Bob Spiro, and Rod Heelis, called SAID, or now SAPS. Anyway, don't worry about the acronyms and all that. So anyway, so we want to thank you for coming up here and telling us all about the aurora and the Helio Big Year. So.
Hi, thanks so much, Mark. It's really great to be here right after such a spectacular event. I want to acknowledge my support from NASA for Aurorasaurus, also NSF, and the New Mexico Consortium. And so the idea today is to take you on a tour of the Helio Big Year, and we will roam all over the heliosphere basically and get to know it and have fun in the process, continuing the fun that you all had on Monday. So how about that eclipse? Yes, amazing, really, really amazing. So I wanted to put it up front here. I am an aurora scientist, but I'm really excited about the eclipse, and especially the opportunities for participatory science with that. Yeah, if we can cut the lights a little, it'll look better.
Let me see if I can do.
So, oh, okay.
Yeah.
I have the.
Let me see if I can do this without.
I have the image credits on here, but we just transferred fonts, and so some of them aren't showing up. So, but the photographers are on there. And there is a NASA Flickr site actually where people can upload images that they've shared with NASA, and these are some of them that are already uploaded. A lot of that is the work of amazing astrophotographers and amateur astronomers. So we see photographs in different resolutions, different exposures. I'm not a photographer. I didn't take any amazing photographs like this, but I'll tell you what I did do. But on the left, you see the solar corona, the solar wind. In the middle, you see a little bit of the diamond ring effect of this light that's going through the edge of the moon as it's eclipsing the sun. And you can also see, maybe I have a pointer here that you can see some of the prominences which are tied to the sun and visible in this beautiful kind of red-pink hydrogen emission from the chromosphere of the sun. And so I didn't even know that we would get to see that. This was my first experience in totality. You can see an image a little bit later on the right-hand side here. I think this image is also from a different location. And so that starts to give you an idea of how these things change. That was another impression I had of how short it is when we are able to see that. And so we'll be talking about how that ties in and science that people can do, everyday people can do throughout this and throughout this whole time period we're calling the Helio Big Year, which I'm about to tell you about. So just to review a little bit, I'm sure Mark went all over this on Monday many times, but just really briefly, like, isn't it amazing that we get eclipses and that they just happen to work out so the moon is the right size to block the sun, and why that happens? Also, why it doesn't happen every single month, because the moon's orbit is inclined a little bit, and so it does not repeat that often. So we're really just in this sweet spot, and very grateful that we got to see it. So I have this talk arranged in a few rough acts here, talking about how the sun touches everything. Raise your hand if you feel like it touched you. Yeah, it really was breathtaking to behold and experience. And we don't always get that in heliophysics. It's not always so tangible, but there are a lot of aspects that are and are quite exciting. So I'll talk a little bit about what is heliophysics and the big year. I'll talk about what is public participation in science, and then also what are some of the open science questions. All right. Before I do that, I will talk a little bit more about my background, since I'm here at a college, and this is kind of the grad student to early career portion of my career. And then I'll back up a little more and talk about my college experience. But I am a very just amateur aurora hunter. We have a really professional aurora hunter in the back there, Vincent Lidvina, who's a graduate student at the University of Alaska Fairbanks, also an amazing photographer. But what I worked on initially after actually, this image in the center bottom here, this is a rocket. The nose cone's not on it. But as Mark mentioned, I got to work on a sounding rocket experiment that flew above the aurora, collected particles and waves, measured particles and waves that cause the aurora. That was what I analyzed for my thesis. It was really hard to figure out, but it was a really great exercise in problem solving and looking at the data and looking at the hardware and communicating between, kind of pure scientists and the engineers who are making these, building the instruments largely. And then I went on to Los Alamos National Lab, where I started as a postdoc and then became a staff member and a team leader, and also got to build satellite instruments, both for NASA and for DOE payloads at geosynchronous orbit. And Los Alamos National Lab is a place that has done a lot of basic science and discovery in this area, and also contributions to national security for that reason, because we need to understand the space environment in order to validate things like the Test Ban Treaty against testing nuclear weapons in space. So there's a lot of opportunities to do hardware, and satellite hardware projects are larger and longer term. This is a calibration lab here in the bottom right, and that was really fun and exciting work. And then one day I got this idea about what would become Aurorasaurus, and that began to take more and more of my energy. So that's what I'm primarily doing now, but this is also was a really great, exciting time to work on the hardware. Software is also difficult, that's what I've learned. But backing up, When I was an undergrad, I actually was basically weeded out of physics. I had no interest in physics after I took it in my freshman year. This is Ruth Skog on the left. She was my mentor, and I got a really great summer research job, way better than Dairy Queen, where I had worked the prior summer, and introduced me to doing physics in a hands-on way and what that meant to ask questions about why things are the way they are. And in that case, we were doing hands-on experiments with magnetic fields and currents in inducing magnetic fields by putting current through kind of a large frame. And we were doing that in order to calibrate an instrument that would fly in space and measure the magnetic field out in space and associated with the aurora. So that was really cool and interesting. And I was able to keep taking physics and graduate. And that was also thanks to the Washington Space Grant Consortium. So some throwback pictures there. So just going on here to what is heliophysics. So heliophysics, the study of the sun and its effects throughout the solar system, kind of graphically illustrated here. Really also another kind of movie about that. So the sun gives us not just light, but charged particles coming out in all directions in the form of the fourth state of matter, this heated gas called plasma. They follow the sun's magnetic field, which is constantly varying, and interact with the Earth's magnetic field, which is a little more well-behaved since we have a North Pole and a South Pole, and it's kind of arranged like a dipole magnet. That energy gets stored in the Earth's magnetic field. It kind of transfers in, gets stored, and then ultimately released in a ring around the North and South poles, where it lights up the atmosphere when, under certain conditions, it impinges on the atmosphere and excites the constituents of the really kind of edge of space upper atmosphere. So I'll talk a little more about aurora later, but that is part of the heliophysics of our local system. This is a great slide I borrowed from my colleague who showed it this morning in the science meeting we were at and adapted from Larry Kepko. So heliophysics is science, a new science and new term, actually, science of connections, and both fundamental and applied open questions. So this image on the left kind of refers to the connections between heliophysics and earth science. You know, that we have the charged upper atmosphere of Earth, as well as, you know, connections to the more normal air that we breathe and weather systems that we're familiar with. So there are open questions about how to connect and model that whole system. As well, in connections from heliophysics to another area of NASA planetary science. So many of the planets have auroras and magnetic fields and atmospheres, but not just like us. So there's a whole field of comparative magnetospheres and understanding how the sun's influences those other systems that are quite weird and interesting. So it's a good way to test the theories that we have. And, you know, we can more easily sample our own magnetosphere and magnetic field region and our own charged ionosphere, the upper region of our atmosphere. And then also compare to other systems, especially like Jupiter and Saturn, where we've actually gone and sampled their magnetospheres. And there's some really cool upcoming missions to do more with that. And then, of course, there's also connections between heliophysics and astrophysics. You know, we are living in the bubble of the sun's heliosphere that goes out and connects to the interstellar medium. My favorite oldest spacecraft, Voyager 1 and 2, are out here beyond the heliopause and out in the interstellar medium nearly, I think now. But there are connections to other stars. Are they like our stars? Do they have variability like our stars? And what are the implications for life on other planets, especially? So really interesting questions in all of these areas, as well as in the applied areas of how the sun's activity affects systems on Earth. We call that space weather, systems on Earth and in space. And that's really important as well. So moving on again to what is the heliophysics big year? Let's see if I can make the little, okay. Well, the heliophysics big year is the name for a public engagement campaign that encompasses these multiple aspects, this kind of Venn diagram here of the fact that right now, from last October all the way through 2024, we have these 2 eclipses. We're also at a time when the sun is really active. We have participatory science projects for both of those aspects, as well as heliophysics has really exciting mission targets during this time as well. Specifically, one of our flagship missions, the Parker Solar Probe, that is going as closer to the sun than ever before. I want to say within like 4 or 10 solar radii. It's getting to its closest approach at the end of 2024. So that's going to end the heliophysics big year, and we want to invite people to participate. The term heliophysics big year, I actually came up with because it's like birding citizen scientists, citizen science. People go out and kind of take a personal quest for how many different species of birds they might be able to see in a year. And so there is an analog here to participating in these projects and the public engagement campaigns around them. When Nikki Fox was our heliophysics director, she wanted innovative ideas, and we pitched her on this, and she said, yes, I love it. Can't do her accent. But she said, I love it, and we're going to do, all the things with that beyond just citizen science, including the communications as well. And so we have the 2 solar eclipses, but, we're not done with the heliophysics big year at all. We're just ramping up to more, and there's a lot more science going on with the data that was just collected. So I'm excited to talk about that. It's also nearly solar maximum when the sun is really active, giving us larger storms. This is especially good for my Aurora project, but other projects as well have a lot of variability and excitement during solar maximum when the sun has more activity that will drive larger auroras on Earth. All right, and solar maximum and minimum come around every 11 years. So it's a gradual change, and we're already very active. In terms of public engagement, there are communications for heliophysics has some monthly themes. And so I wanted to put these coming up. I don't actually know exactly what they're going to do with all these things, but if you have any ideas, you guys have some great outreach activities here, and we'd be happy to work with them or get the word out more about heliophysics, space science at this time too, and tie into the big year to get it out to more people. So that would be really exciting. All right. And here's a nice, cool video about the Parker Solar Probe. Obviously, an artist's conception of this, but it's very cool. So I wanted to play this. It's been a while since I've played this, so my narration is not great, but you can see the orbit, you can see the spacecraft. There's of course some crazy engineering so this thing doesn't melt as it gets close to the outer corona of the sun. I haven't yet seen, something like an eclipse picture. We're going to see more corona pictures with like how close Parker Solar Probe is going to get. That would actually be kind of cool to see as well. Now that we have these beautiful eclipse pictures from Monday. All right, I'm going to make sure I don't talk too long here. Okay. All right, so yeah, so why is a solar eclipse a really exciting time to do science? We actually can't see that corona with satellite instruments very well at all. And so you can see this big gap here. We can look at the sun in different wavelengths, and we need to look at the sun in different wavelengths because there's sort of different depths and different regions of the sun and how they are working, how they're driving this activity. We are, of course, trying to understand the variability of the sun, how large events and small events can happen, as well as some really interesting questions. The outer corona of the sun is very hot. It's 1,000,000 degrees, and the surface of the sun is, only a few thousand degrees. So there's a lot of interesting physics happening there, and without being able to actually see what's happening in this inner region as the corona is born and evolves and accelerates, we really can't understand that fully. So this image kind of shows that adding the visible corona will bring more understanding. But then there's how you do that. And with the eclipse being so short and, we can't put a professional billion-dollar telescope all along the path to stretch out those observations. We can do some things, like NASA actually did fly some research planes to take really longer observations of the corona. But we're turning to citizen science, actually, and people. 100 years ago, people were just like guarding the telescopes. There's a really fascinating history of science being done during solar eclipses. I'm not going to get into all of it. This is one little history slide here, but 100 years ago, people were just kind of guarding the telescopes, and the scientists would go to some exotic location and observe the corona, observe these amazing things we got to see, and try and figure out what that was. Was it a brand new element? Was it heavily ionized iron? Heavily ionized iron is actually what it was. Yeah, now people can actually use instruments, even, starting with your cell phone, your digital camera, or telescopes that amateur astronomers have to make observations. This slide shows a drawing of a coronal mass ejection during an eclipse, which I think there was quite a bit of possible, all last week there were CMEs, it seemed like all the time. I don't think one happened yesterday right at this time. Somebody correct me if I'm wrong on that, but there could still have been maybe something small that we didn't notice yet in our couple minutes of individual observations, but we will see a lot of features and a lot of dynamics still. There's other kinds of activity that aren't quite as large as that we're going to study. And we do have, this image is cool because it shows you some of the dynamics. Sorry, I don't have the exact source of this image on there. I should, because I don't know it. But a corona image taken from a coronagraph type instrument. So that blocks the sun, and then you can image the corona, but you can't get very close to the actual size of the sun. So, but you can see how large this activity is. And yes, there's, kind of a serendipitous opportunity to observe the corona. And anytime we have that, especially over such a populated, path as this one, it's very exciting. So that shows, that was me trying to talk about some of the open questions in the corona, why it's so hot, how it is born and evolves. Those are questions that these citizen science teams are going to be working on with data they collected. And then there are many other open questions still in heliophysics, such as what is, how this thing, which is the that Steve type of aurora that Mark mentioned, the normal aurora is here to the north. And then there's this mauve streak overhead east-west. There's these vertical green auroral-like pillars. There's even some really funky little beads of aurora that really shouldn't happen like that. So we're still trying to figure out when and where things happen like this as well. So you can help. And any of you who are not science, you don't have to necessarily go to grad school and be an officially trained scientist to be asking questions about the universe that are really valid, interesting questions that can move us forward and that you may have. I'm sure everybody here has great questions about the eclipse or some other science aspect right now. So this is a quote about that I like. By an environmental scientist, and she's talking about the ethics of with respect to environmental science. And so, but also it means I see it a lot with our participatory citizen scientists. I get folks who are like, here's my log of aurora activity and what can I do with that? And I like to respond with this, you're being a scientist. And, then we also go on to, or Mary O'Brien goes on to talk about what kind of questions we ask is really important at that point. And looking at the bias with respect to the questions that you ask is really important. And if you're a professionally trained scientist, you kind of go to school and spend many years on some particular areas. Whereas people who are enthusiasts across different areas. They don't care about the boundaries. And it actually is a real advantage as far as asking interesting questions also. So a little bit more about citizen science. This is a book that I really like, actually 2 books that I really like about it. But it's organized research in which members of the public can engage in the processes of scientific investigation, asking questions, collecting data, or interpreting results. It may not be building your own satellite instrument, but it's still valid data that is collected. It is really unique in that it can work on such a massive scale and generate high quality data if you build in appropriate data quality controls and you ask appropriate questions given the limitations of this kind of data. For instance, you can have like a population bias that more people are looking at a particular species or something like that. And in heliophysics, we have a public that loves things like the aurora and eclipses, and so it's really a good match there. There's also projects, I'm an amateur mycologist, and I like a couple of other projects. I like nature, so I like to participate in iNaturalist and eBird. I'm not a big birder, but those apps are so good now that they can hear the birds and I practically identify them for me. And in the case of iNaturalist, it can look at different species and say, is this your mushroom or something? And I can say, well, I think so. And then the naturalist actually goes and confirms that. You might have some specialist talking on the other end of that app, actually. So it's really cool, something like that. That's a little more than we do in Aurorasaurus. I really admire what some of these larger environmental projects do as well. Yes. Okay. NASA is into citizen science. We have official policies encouraging citizen science. We actually have more than 30 projects that are open to the public, a bunch that can be done anywhere, by anyone. Definitely do not have to be a citizen per se. We are going away from that term. But a lot of these projects help analyze data that NASA collects, because we do have big satellites and they collect a ton of data, and there could be things hidden in that data that we are missing. Algorithms would miss. The human eye is much better at finding the really unusual things. You can't write an algorithm for what you don't know, but you might notice it by eye. So that's really exciting. NASA also has a bunch of citizen scientists who've been co-authors on papers. There's another platform called SciStarter. I wanted to mention them because they're kind of a clearinghouse platform. They work with all kinds of other groups, from Girl Scouts to libraries to NFL science cheerleaders, Discover Magazine. They're promoting 1 million acts of science in April, so you all can still contribute. You can sign up for an account and track those there. Or you may have already contributed if you did any citizen science during the eclipse. And they just had a live sort of discussion about eclipse citizen science results that's available. Did anybody do any citizen science during the eclipse? Possibly. Some of you. He wanted to. Yes. Awesome. Okay. So these are the projects that in the Helio Big Year, which does continue. The top row are the eclipse-focused heliophysics projects. And then the second row are things that involve other senses and other fields, really. And then the bottom row are all the projects we can continue to investigate, as well as some of these on the second row. They're still ongoing beyond the eclipse. But I wanted to show you there's a whole range of projects. There are some projects beyond heliophysics, and again, like involving eclipses, exoplanets, things like that. Some of these projects are ones you can do indoors anytime, and some of them are ones where you're actually observing or taking measurements. So I'm going to talk a little more about these, and I'm maybe going to speed up a little bit. This is a little montage of people, different experiments and their annular eclipse, kind of pretty pictures. This is, for a lot of these teams, the annular eclipse was a good warm-up. This Soundscapes project, they're deploying sound recorders in nature. The Dynamic Eclipse Broadcast Initiative, there is some serious telescope computer, data acquisition during the annular eclipse, as well as the total solar eclipse. The Sun Sketcher project is one I participated in with my cell phone, and they take just really coarse images of those diamond ring or Bailey's beads effects. And then there's the HamSci project for hams, where the annular eclipse is totally game on as well, because the moon's shadow in the upper atmosphere, makes it dark, and also changes the charging. And so going basically from day to night so quickly induces some instabilities, and the whole amateur radio community was looking for changes and globally kind of distributed for that. So they had a whole contest with 1 million observations, actually, to see how many contacts you can make during an eclipse. So if you are a ham, really into that. This is where I was, and these are not the highest quality images, but they're mine or a friend of mine's images of what was going on where we were in Lomita, Texas, at a small event. But there was a guy there, Rahul, who's actually working for NASA Johnson. He is a mission control Artemis engineer going back to the moon, and he's an extremely keen, awesome astrophotographer. So he was out there with multiple cameras and telescopes and his own little tent and his computers and airdropping photos to people. This is a low resolution version of one of his, a still from his video. Some of the prominences that we saw from that location, also some of the cloud that we saw. I think there's probably post-processing, you can get rid of some of those. And so, yeah, it was really amazing to see his setup and experience, somebody just, to see it in person. I've seen it in person with auroras, but had not seen that with for an eclipse citizen scientist as well. And I did a few outreach activities and just kind of talked to people about eclipse stuff. So that was fun as well. I'm happy to talk more about that, I don't know, later on if you like. Okay, but I'm going to talk a little bit about what NASA funded for, both NASA and NSF actually, funded for measuring the corona. And we funded a number of different projects at different resolutions because there are all of these different features and we don't understand any of them fully with the corona. So the Eclipse Mega Movie is the one that just, if you have some really awesome camera observations, they are looking for those. You can still upload those, and they're tracking especially polar jets and activity sort of from that side. And then there were 2 sets of telescope teams, which I don't know how many people were in Eclipse Mega Movie, probably thousands of images for sure. The Sun Sketcher app has a different focus. It's the low resolution images of those Bailey's beads, but they are going to work out from the precise timing of, I think they got like 29,000 images. They're going to try and work out better the precise timing of when those beads show up. They think they can do the math and work out the size of the sun better than we know it currently. So that's actually really has other implications for all kinds of other physics and a really exciting new sort of project. And then there's the 2 projects on the right here with telescopes and training provided to teams. Citizen Kate is looking at the corona in polarized light, so you can work out some of the really invisible magnetic structures. And the Dynamic Eclipse Broadcast Initiative, I think they had 80 teams, hundreds of people in total. They were streaming the disk of the sun and then collecting observations in a specific way during totality. Actually, some of their folks were on the path and some were not, so they could track features on the disk of the sun as well. So a really great cadre of projects there. Taking observations such as this, and you can see, let's see, this one's actually a movie. You can see that the thing on the right here is a model of what the corona should look like. And it's a really fancy data assimilation using, remember, we can't see the corona. So they had to build a physics-based model and use all the rest of the solar observations that we have and build this prediction of what the corona and the features under that would look like and run it in real time and run it along the path of the eclipse. So following the sun. So if you actually want to see what their corona prediction looks like compared to where you were, you can click on the map. They have a really cool little widget and it will show you their prediction. And you could compare that to your image. I don't know, there's more work to be done there as far as like, this image on the left is, the resolution, the exposure time of different images. They're going to work quite a bit more on comparing how well their model did. But you can see a few of the features like this little kind of gap here. I think you can kind of see, and some of the sort of wings of the corona here and streamer sort of features. It's not looking so good at this frame, but I think I was looking at it earlier. I was like, oh yeah, there's that little gap. And, I don't have the exact comparison here, but it's really interesting. And also it shows you how dynamic the corona was expected to be, which just reinforces people being kind of the force multiplier for the observations all along the path. All right, I got to speed up. There were projects looking at effects on wildlife and life itself, eclipse soundscapes, really cool projects. Projects that you can still get involved with after the eclipse, GLOBE, which is really, they look at temperature, clouds, land cover, mosquito habitat, all kinds of different things, really well set up for classrooms. It's a very large earth science project. And then the HAM-SCI project that I already mentioned, their festival or contest for making contacts during the eclipse, as well as Radio Jove, which does not just measuring changes in the atmosphere to the eclipse, but it also measures changes in radio signals from as far away as Jupiter. So another really cool kind of multi-purpose project. And then there were a bunch of college student teams that did weather observations, and they launched weather balloons every hour, like from dusk till dawn and during the eclipse day. So those teams got a lot of engineering experience and really well-led project out of in Montana. I'm going to get it wrong. I think it was Montana State University. But really cool project there. This shows the visible cloud image that shows the eclipse itself darkening. I don't know if you can really see it. It's a little hard to see, but you can see a little bit of how, when it gets dark, the clouds dissipate a little bit because it gets colder. And then you can see where, that we largely, I think, got very lucky. And you can also see the situation in Texas, which was quite touch and go. Yeah, more or less. Okay. We have other non-eclipse projects, ones where you can observe transiting exoplanets, even if you do or don't have a telescope of your own. Ones in which people photograph these really cool electrical phenomena that happen above lightning and big thunderstorms. I know there are folks in Oklahoma and New Mexico, and I imagine Texas, that are storm chasers and perhaps contributing to this project. There's an upcoming, actually, I shouldn't say upcoming because I think they've already deployed some magnetometers. The Easy Mag project, they're going to deploy ground-based magnetometers that can measure the signals from all this space weather on the ground in conjunction with an upcoming satellite mission called Easy. And that's being deployed to high school teams largely throughout the US. So that's really exciting. And then there are a bunch of projects you can do anytime, anywhere, involving listening to waves in the magnetosphere. That's the HART project. That project has a really cool backstory that I won't get into. The Sun Grazers project, which is a long-standing 20-year-old project, and people have found comets in this data. They just found their 5,000th comet, which is way more comets than people have found in any other way. There's a sort of a couple of projects on the Zooniverse platform where you can use satellites and look for things such as solar jets. So continue on there, and that's a really great project platform builder. You might have a citizen science project in mind with satellite data, and that's a great tool for that, the Zooniverse platform. They have like 1 million people will come check out your platform. So, all right, now I'm going to talk a little bit about auroras briefly. So these are some images from an amateur aurora hunter in 2021. You can see the aurora very significantly. You might also notice this person is, well, they're pretty far north in the US, and they're one of the really lucky ones who lives somewhere where they have a north-facing view and a dark sky location. Yeah, really great opportunities. Not everybody has these opportunities for seeing aurora, and they know when to go out and look. what causes aurora? You know, I think many of you guys know this already, but just to kind of connect the dots here to, these emissions from the sun, these large bursts of radiation, they travel through this solar wind, this corona that we just saw. They might come and energize the Earth's magnetosphere and then drop and deposit their energy in our upper atmosphere, where they can actually light up give off specific wavelengths of light that that correspond to the colors. So different altitude regions give off different wavelengths. So you can see oxygen, sometimes even below that, you can see a molecular nitrogen, a super cool pink layer. Above that, you can see a tiny bit of blue. And then even farther above that, you can see some red that is also due to oxygen, but a different chemical emission at a different, because of the higher height and the different density up there. This animation was made by a citizen scientist, really awesome citizen scientist named Jeremy Kazub from Canada. There are different types of aurora that people report to us. They happen at different times of the night. Different physics is involved. You could probably come up with many different sort of categories. These are the sort of basic categories that we ask people about on our website. And again, we're trying to take advantage of these communication methods that we now have, because we really are pretty data limited in space physics, especially for predicting when the aurora is going to happen. And there's a couple reasons for that. One reason, the sun is so far away, 93 million miles away, and we can watch the sun really well, but we can't actually watch a really critical invisible quantity that matters for how much energy comes in and how much aurora is driven. So we can't really detect the magnetic field of the solar wind, especially when there's a large coronal mass ejection. And we can't detect it at all until we have what are called kind of in situ measurements, where we actually sample the magnetic field. And we only have a couple of satellites that can do that, and they hang out at a specific location that is about 1 million miles upstream of Earth. And on average, the solar wind goes 1 million miles an hour. So it gives us about a 1-hour warning of how strong that incoming material is going to be. And then we have some models that can predict how strong the aurora might be. This photo is by Vincent, who's in the back. And I can talk more about it. I'll probably skip it now since we're in Texas and you might not get to see aurora that often. But I'm happy to talk about how you could see aurora more. And you can check out our website, Aurorasaurus, for more information about that. I do want to get to the little movie about the Steve discovery, citizen science discovery. We have some blogs about aurora and space science topics. If anybody wants to collaborate on this, we're interested in that as well. Aurora really is important to tell us for both the fundamental and the applied reasons. It's significant, the aurora can have significant effects on our technologies. So we really do need to know what it's doing, where it is, how it behaves, as well as in terms of astrophysics, auroral observations, with JWST or other telescopes could tell us potentially that a planet has an atmosphere and a magnetic field, and that those are both critical to why we are protected and can live and breathe here. So it's really great.
People were out observing the aurora, and they started.
Okay, I've sort of screwed it up here. Not sure why. I'll try it again. It's not going to show correctly. You get the narration at least.
Out observing the aurora, and they started noticing something that was
Something.
overhead as well when they were seeing the aurora far to the northern regions. It was unlike most aurora. Talked to the scientists, we didn't know what it was. And together they said, we'll keep taking observations and we'll call it Steve in the meantime. Steve is mostly a very narrow purple arc, and sometimes it has these little green features that go along with it as well that are kind of like waving fingers or a picket fence. That means that there's plasma physics happening up there to cause that light and to make these little discrete features that we don't understand yet. We now have some satellite observations from the ESA satellite called SWARM that show that Steve optically is associated with a very strong flow in the particles in the ionosphere, the upper level of our atmosphere. Steve is important for a number of reasons. It's really exciting that people armed with cameras all over the globe can capture something that we didn't fully understand and shed new light on that. It's also really exciting that this happens further to the south where there are more people. So it might be a kind of aurora that more people can see than the usual kind. We're now able to look up at the sky and see things about the aurora and this subauroral region that we never understood before. And then we can correlate that with our traditional observations and lead to greater understanding.
All right, sorry, it did not display correctly there. But I got to drink a little water, so that's good. These are some of the examples of Steve observations from one of the aurora chasing groups, the Alberta Aurora Chasers. They're the ones who named it Steve. That's a reference to a movie called Over the Hedge, which is a little animated movie in which a little squirrel, coincidentally voiced by Steve Carell, the hedge pops up in their neighborhood and they say, what is it? We don't know what to call it. And the squirrel says, just call it Steve. So it's not so scary. But it's not an entirely new thing. So when we looked at the satellite observations, we actually found that it is this subauroral ion drift that has been recognized for 40 years from satellite observations. What's new is that it was never known to be visible. And then there's also like extremely old extremely old photographic evidence and description papers of this being seen and described before that we also did not actually find back in the 2015 to 2018, all the previous literature reviews that the whole team did. We didn't find this, but a citizen scientist out of Germany had noticed this, had studied these other observations, which are Carl Stormer's papers, and he had taken photographs and basically described it to the extent that he could at that time. And so it's not a totally new thing. Some of the photographs were seen, but they didn't know what it was. And then some of the satellite observations were seen, but they didn't know it was this thing that had been seen. And 100 years ago, it was called feeble homogeneous arcs of great altitude, because it actually is, I call it aurora, but it's happening in a different way than this energy deposition that comes down in altitude. It's a really strong flow that's exciting a color and different broadband emission of color in a different way. So that's still being explored. How Aurorasaurus works. I know this is the burning question you all are left with here, but basically we have a map, we have a website. You can report, you used to be able to report on Twitter, and that no longer works because Twitter no longer works very well. But you can report if you've seen it or not. Null reports are useful, especially if the model might think that you are able to see it. If the model thinks you're able to see it and you're in a clear sky region, that's useful. Or if you're in a cloudy region, you can help out others. We also have alerts based on these reports. And yeah, I just kind of wanted to come full circle with this final video here. So this is the end of the talk, but really want to invite people to join us. Keep checking out Heliophysics. You have such a great place to do that here. And there's many ways to follow NASA Sun and or check out the different citizen science observations and kind of get to know our local star in a different way. And how it protects us, how Earth protects us, excuse me. This animation, actually, I think it's more of a model, but it's a really cool visualization. But, showing here how basically the solar wind is streaming past Mars and not protecting it here, also stripping away the atmosphere. That's another thing as well. But here, showing kind of a different view of the protection of Earth afforded by our magnetic field. So I will end with that. It's a great time to be a heliophysicist. Thank you. I would love to take questions. I understand it's already 8 o'clock, and if people have to go, they have to go. That's okay. But if there are questions, I'd love to take questions. Sure. Mm-hmm. Yeah.
Came in one morning and said they had filmed Jupiter overnight. And they went, they just in their backyard, they had a telescope, filmed Jupiter. They came in the next morning, they woke up and looked at their astronomy blog. And someone said, did anybody see a flash on Jupiter?
Mm.
And so we looked at his video and he captured a comet crash into Jupiter.
Cool.
He was the only person in the entire world.
Yeah, that's awesome.
And they ended up using it in scientific, and this was just a student, in my astronomy class. I had another student that wanted to do a research project and wanted to look for variable stars. And so we looked at the photometric database and the astronomy database and found a variable star. And actually now his name and my name are in the astronomical database as the discoverer of a variable star. So these are the kind of things that
the variable star observers, the amateurs, they have like a whole high school class where you can take a class to learn how to continue to like observe variable stars and get a publication out of it. They have a whole like kind of amateur journal of variable stars. It's really cool. Just one like our star that has variations. You probably might have a more technical. What is a variable star? In the brightness. It varies in brightness.
So a variable star is a star that actually changes its light output. And what it does is it expands and contracts and expands and contracts. And there are various reasons that stars are variables. One of the things that when they do planet searches, one of the ways they find planet searches is when a planet goes in front of the star dims and then it comes around and it brightens again. That's one of the ways, like for instance, TESS and various extrasolar planet searches find that. So when, for instance, one of our Kepler, for instance, one of the discovered 5,000 extrasolar planets, they have to determine whether it's actually caused by a planet going in front of the sun, or it's actually caused by an actual variable star that is changing its output as a variation in its output. And so this is one of the, it's just, it's
also a really great topic for citizen science because the big telescopes are not really gonna, like people in their kind of amateur smaller telescopes can find those things. And then that might be a target for further study with like a bigger, more expensive telescope time. I have a couple of posters from the eclipse, Tyler Nordgren posters. So if anyone really wants to ask me a question, you might get a poster. Yes, what's your question?
Here. What did I write? Oh, yeah. Well, do stars have any effect on the sun?
Do other stars have any effect on the sun?
Yes, the variable star.
I mean, the sun is a star. Yeah, so there are some like double star systems and that sort of thing. I don't know too much about it, but they have magnetic fields and they probably interact. And I don't think we know anything about that largely, right? Because that much farther away, we can't,
Yeah.
it's like really coarse, but yeah, I think they're probably, does anybody want to add more to that?
I think the main thing would be if you had a really big supernova close by. Fortunately, it's not going to happen. So.
Mary is our astrophysicist. She probably has the best.
So, and in most cases, with the exception of what Dr. Hairston was talking about with the supernova, the stars are too far away to affect Mars.
Right, but there are other-
Stars gravitationally bound. You know,
Yeah.
You know.
We're all bound together in the galaxy together. We've done the other stars beyond that.
One more person there.
I'm not in physics, or I'm actually in a business school, but you had a question on the sun's surface. Is that the only part that's burning? So what's inside the sun and, you know, how does it not go out and start burning out? It just burn on the surface.
I had a premonition. People would ask me this. Someone else can speak to this, but I'm going to kind of say there's a whole dynamo, a fusion in the sun, and it actually takes a really long time, thousands of years, I think, for the photons to escape the sun. And there's many different kind of regions, and this is really not my specialty. So I will be happily corrected or added to.
Just to add that what we see on the surface of the sun isn't burning, that's actually, it's just really hot. And it's really hot because of the energy it's generated from the conversion of hydrogen to helium by fusion in the core. Because the core is sufficiently dense and it's sufficiently hot so that the really improbable thing of hydrogen ions coming together actually happens inside of the core. And so it takes a long time for that light to get out. The latest models I've seen are something like 10,000 years. We used to say a million.
Yeah.
We used to say a million, but the time is getting shorter in terms of the time to get out of filter the light to come out of the core. But it starts off as gamma radiation. And as you move further out, it's now turning into something that's producing visible light, more like the filament light.
Yes.
Can you talk a little bit about what you did for your thesis for your PhD with sound?
Yeah, I worked on part of an experiment that was designed to, I specifically worked on an instrument to measure the really coldest thermal electrons in the ionosphere, which is a super hard measurement because the rocket moving through this charged particle environment also changes it. And so you can really, it's really difficult to get down to as cold of an energy as we want, like, 1 EV, 10 EV, certainly less than 1 EV. But I had a little, my analysis was to try and understand the data from the thermal electron detector. And I'm still a little bit scarred by that because it was a really hard project. But there were other particle instruments, like more typical energies of what is precipitating, we call it, to cause the aurora. And that's like a different range of energy, different range of detection phenomena. And those are more, those types of instruments called electrostatic analyzers. Basically, there's a voltage applied to kind of an inner plate, and there's an outer plate, and the particles come in, and by the changing voltage, they curve around, and they can be detected by a microchannel plate, which is like the sensitive part of a night vision goggles, that sort of thing. And then that signal gets amplified and counted. And then you can do that in, different directions, and you can understand a lot about the particle distributions that are causing those types of aurora. So that's what I worked on later, like the slightly easier, higher energy, but still pretty cold plasma measurements for both electrons and ions, and some with some species differentiation as well. Yep.
We are actually building instruments for sounding rockets that will be launched next year. Instruments for satellite projects. We currently have 9 satellites in orbit around the Earth with our instruments on it. We've been launching satellites since 1965. We have over 60 experiments that we put into space here at UPD, including the Moon, Mars, Venus, Halley Comet. The last one we launched was in December 2022 for the space station. So yeah, so we do some really good stuff here.
And the hardware, especially, it's a really employable skill. So getting those skills as well.
How much is ground-based, also satellite-based observations affected by all the junk we have up there and all the Starlinks?
Yeah.
Tens of thousands.
Yeah, well, I would say that in heliophysics, we don't have as much problem as the astronomers do with like streaks through their telescopes, and they really are looking so much farther away that you can really mess up a bunch of pixels.
They're really
Yeah, they're very upset about Starlink. Starlink as well, a year or so ago, there was a launch, and those things, they're kind of flimsy, right? So they actually, a launch failed, like 40 of the 50 satellites re-entered because it was launched basically right between 2 geomagnetic storms. But the interesting thing is that they were pretty small geomagnetic storms. But they changed the density of the upper atmosphere, and they were launched in a particular way that they were still pretty low in altitude. And so the drag was able to affect them and bring them down more. So there's increased possibilities for all kinds of things that are problematic. Yeah. And
SpaceX needs to subscribe to the space weather forecast system.
And I think they've also modified perhaps the insertion altitude to be a little more resilient for that. But, and then there's also like things that are launched, they have requirements for how long they last and how they re-enter safely. And there are requirements on that. And then there are other things that happen also.
Yeah, nowadays when they launch a lower, it is actually required to have propulsion so that they can control the reentry and they can reenter and have it burn up. I mean, we're putting in, what did we put in, 3,000 in the last 5 years or something like that.
Shut it completely.
Okay, don't shut that.
It'll
I
stop
won't shut
recording.
All right, but thank you so much. I'll stick around a little bit. I'll give out some posters, and really happy to be here. Thanks. I'll let you mess
I'll
with
take
that.
care of